Let's think about how we can derive general formulas for sums of particular pattern. So for example, how can we compute the sum of the first 100 numbers? So numbers from 1 to 100, if I wanted to add them up, how would I be able to do it? Well, the general approach is, when you look at this, is to think about adding everything in a row. So 1 plus 2 is 3, then plus 3 is 6, and plus 4 is 10, and so on and so forth. But this is obviously going to take a while. So instead, let's think about how we can add these numbers to themselves differently. And one interesting thing to notice is if I take the first and the last number and add them together, I'm going to get 101. Right? 1 plus 100 is 101. If I take the second number and the second to last number, 2 and 99, I still get 101. And if I proceed that way for all of the numbers, I'm going to get 101 all the way down through to the middle two numbers. So instead of adding in a row, I'm going to add from beginning to end and sort of curl the sum down this way, kind of like a rainbow. So what I have is every pair of numbers, one from the beginning, one from the end, adds up to 101. And the next thing I have to think about is how many of those pairs are there? So how many times am I going to actually produce this summation? Well, I'm pairing the numbers up 2 at a time. So amongst 100 numbers, there are going to be 50 pairs, right? It's going to be 100 numbers divided into pairs, divided by 2, so 50 of them all together. And now, instead of adding 100 numbers in a row, all I have to do is multiply two numbers. 101 times 50 is 5,050. This famous problem is actually famous because there is a legend that goes with it that Gauss, a famous mathematician, when he was 12 years old, was so smart at school and in math that his math teacher, just to keep him occupied, gave him this problem to solve, and he came back with the answer just a few minutes later, having derived this particular method. The funny thing is probably the teacher wasn't actually able to really brute force double check this answer because this was back in the times before calculators. Now, we can actually generalize this method because there is nothing special about 100. We can go all the way up to n. So the pattern will still hold. If I add 1 and n, I'm going to get n plus 1. If I add 2 and n minus 1, so the second last number, I'm still going to get n plus 1. And all the way down, I'm going to get a bunch of n plus 1s in the exact same way. So I have n plus 1 as the total of all the summations, and now I just have to think about how many of these summations do I have, and there's going to be n divided by 2 of them. So altogether, I have n plus 1 times n over 2. Now I'm skipping a slight step here in showing that it doesn't really matter if n is even or odd, because really when I'm dividing by 2 here, I should guarantee that I can in fact do that and get an integer. But it's going to work the exact same way with odd numbers as well, because the middle number is going to be only 1, and it's going to be the exactly right number all in itself. So the total sum is going to be this value. So in order for us to be able to use it, I'm also going to rewrite it in the summation form so that I don't have to go ahead and write out all the numbers from 1 to n. So the sum of all the numbers from 1 to n is equal to this expression, n times n plus 1 over 2. So you take the last number you're adding, you're then supplementing it with 1, multiplying the 2, and dividing by 2. Notice that independent of whether n is even or odd, this will in fact produce an integer, because either n is even, and therefore it's divisible by 2, or n plus 1 is even, and then that's divisible by 2. So you're never going to be in danger of getting a fraction on the right-hand side here. Now I can derive other formulas. I'm not going to show you the actual derivations. We will prove them later using induction. But for example, if instead of numbers, I'm going to add squares. So instead of 1, 2, 3, 4, 5, I'm going to add 1 squared plus 2 squared plus 3 squared and so on, all the way up to n squared. Then the formula for their summation is going to look like this. And then finally, if I'm adding cubes, so 1 cubed plus 2 cubed plus 3 cubed and so on, all the way to n cubed, then the corresponding formula will look like this. Now, one thing to notice here is that all of these sums begin with 1. So in order for me to apply any of them, I have to make sure that my sum that I'm considering indeed starts at 1 and goes all the way up to n, or I'm going to have to massage it in some way before getting it into that form, and therefore before applying the actual formula. So let's see how this works out. I'm going to keep my useful sums over here and then go through a bunch of examples that involve summation calculations. So if I'm computing the sum from 1, 2, 3, 4, 5, all the way up to 123, then it's direct application of this formula. So it says I should take my last number, 123, and then 123 plus 1 over 2, whatever this number comes out being. This is again one of those cases where leaving the formula as your final answer is probably more illustrative than giving the final answer as a number. If you have a formula, I can see where it came from. But if you give me some kind of number answer and it's wrong in, let's say, one position, I have no idea where you've actually made your mistake, in the deriving of the formula or in the physical arithmetic. Okay, next up we have 3 plus 4 plus 5 all the way up to 100. So the problem here is I cannot just apply this formula directly because within this formula, the sum has to start at 1, whereas in my case here, it starts at 3. So before I can apply this, I should come up with a sum that begins with 1. So the way that I can massage this expression is to say it starts with 1 all the way up to 100. But in order for me to keep my equality, I know that these two terms are not present here. So I'm going to subtract them out from my expression here, leaving only the terms that actually are in my original expression. So minus 1, minus 2. Okay, so once again, I've added 1 and 2, I've subtracted them, so I haven't changed my actual expression as it appeared before. But now, having this allows me to apply the formula directly. So the sum from 1 to 100 is going to be 100 times 100 plus 1 over 2. And then I better, of course, remember to subtract this 1 and 2, because otherwise I cannot be writing equal sign all throughout. Excellent. Let's take a look at this one. So now I have, it starts from 1, which is good news. I won't have to arrange the first term to be different. It goes up to 20. But what I have inside isn't just the sum of the numbers, it's 4i plus 7. So before I can apply any kind of formula, I have to break this sum up. So let's see, I can go from 1 to 20 of 4i plus the sum from 1 to 20 of 7. And then, using one of the other rules from last class, I remember that I can take this 4 and put it outside of the summation. So in my next simplification, I can have 4, the sum from 1 to 20 of I, plus the sum from 1 to 20 of 7. Excellent. Now I am really in good shape because this sum is exactly of the form that I can apply the formula to. So this summation now, I can apply the formula directly. So I'm going to have 4, don't forget the 4, that coefficient of course remains. And then applying the formula to the sum from 1 to 20, I'm going to have 20 times 20 plus 1 all over 2. Plus, and now of course I have to deal with this summation. And again, remember from last time, here I'm adding a constant to itself 20 times. So this is simply going to be 7 added to itself 20 times. And that is what I'm going to have as the final answer. Again, leaving it in this format allows me to see where your actual reasoning came from. So if it's a test, a quiz, a homework, where you can leave out the actual written answer, make sure you have this kind of full-formed answer before you give the number as the answer, because this shows the reasoning, whereas just the number answer does not. Next up, 3 plus 6 plus 9 plus 12, and so on. So one thing I notice here immediately is I'm not increasing the numbers by 1 anymore. So this is different from the format up here. So I cannot just shift my sum by a couple of terms. I actually have a significantly different sum. But the other thing I notice is that all of these things are multiples of 3. So what is going to happen if I take 3 out as a factor? I take 3 out. What is going to be left of 3 is 1. What is going to be left of 6 is 2. What is going to be left of 9 is 3. And I can see that now these numbers actually do go up one by one, all the way up to, factoring out 3 from 1500 will leave me with 500. Now this is again the summation of the form that this formula can be applied to, but don't forget your coefficient of 3 up in the front. So here I'm going to have 500 times 500 plus 1 all over 2. Good stuff. Next up, I have the sum from 1 to 20, I minus I squared. So I'm going to break it up into 2 because I don't have a formula for the sum of numbers minus their squares. So I'm going to have the sum from 1 to 20 of I minus the sum from 1 to 20 of I squared. And now I'm again in good shape because the first sum is of the form that I can apply the first formula to, and the second sum is of the form that I can apply the second formula to. So let's see how that works. My first sum is going to be 20, 20 plus 1 all over 2. And my second one, again, it's from 1 to 20, so I'm in good hands here because it also starts at 1. So 20 is going to replace the n in all of these brackets. So 20, 20 plus 1, 2 times 20 plus 1, all over 6. Good stuff. What are we having here in the last part of this question? So this is kind of similar to the one we've just done. I can see that there's going to be 2 parts. I can see that I can apply the formula for the cubes to the first part, and after taking 4 out, much like I did here, I'm going to be able to apply the first formula to the second half. My biggest issue here is that I'm starting with 2. I'm not starting with 1, which is where all of these formulas are applicable to. So I'm going to have to adjust for that. How can I rewrite this expression but using the sum that starts at 1? Well, let's think this through. What am I supposed to be, either adding or subtracting here? My original sum started from 2. This new sum starts from 1, which means that the first term is present here on the right-hand side, but not here. So I should be subtracting the first term. So minus, and let me just write that down here, the first term. What is the first term of this summation? Well, I can just plug 1 into the actual general term inside to figure that out. So I'm going to have minus 1 cubed plus 4 times 1. That's the first term in my summation. If I take it out from the right-hand side, that means that I'm going to sort of cancel it within the sum, bring me back to the right summation on the left-hand side. Now I am, in fact, ready to start breaking up this summation and applying the formulas. I'm going to skip a couple of steps here and apply the formulas directly. So I'm going to see that the first summation is of the cubes from 1 to 20. So what I'm going to have is 20 times 20 plus 1 over 2 all squared. Plus, then I'm going to have 4 times the summation from 0 to 20. So 4 times 20, 20 plus 1 over 2. And then don't forget that I do have to actually subtract this last term. So I'm going to have minus 1 cubed plus 4 times 1. And now I am truly done. So this is going to be my final expression. Okay, so again, the key in applying these formulas is just remembering that your expression has to start from 1, go up until a certain number before you can apply it. And then also don't forget that you can break up the sum using the massaging techniques that we discussed last time. Next up, we're going to consider summations that some of you probably have seen in school before, geometric series or geometric sums. So here's the first one, 1 plus 3 plus 9 plus 27 and so on. So the pattern that we notice is that as we move from one term to the next, we always multiply by 3. So what we actually have here are the powers of 3. So if I were to write this in the summation formula, I would have 3 to some power. Now I just have to decide what my index starts with and goes to. The first term here is 1, which is 3 to power 0. So my index has to start with 0, and it's an infinite sum, so it goes on forever. Now, this one is also a geometric series, but now my coefficient or my constant of multiplication is different. So to go from 1/2 to a quarter, I multiply by 1/2. To go from a quarter to 1/8, I also multiply by a half, and so on and so forth. So in this case, I have that I am working with powers of 1/2. And looking at where I start, my first term is 1/2 to power 1. So in this case, my index is going to go from 1 to infinity. Now, there are two types of geometric series. These are the infinite ones, so the ones that go on forever. And then there's the finite ones, so the ones that actually have the last term. First, we're going to talk about the infinite geometric series, and we're actually going to derive the formulas for how to compute the summation of any geometric series altogether. General form of geometric series, just to be consistent with notation, is going to be the one that starts with 1. So it's going to be 1 plus r squared plus r cubed, and so on. So if I were to write this out in the sum, it will correspond to r to power I, where I starts from 0 and goes on to infinity. Okay, so the formulas that we will derive will actually correspond to this summation, the one that starts at 1. And just like on the previous page, if you then have to deal with the summation that does not start with 1, you will have to adjust it before applying one of the formulas. There are many ways to derive the actual formula for this summation, the exact result that these terms will sum up to. I will show you a geometric method for the infinite sums. So what we're going to do is we're going to draw two lines. This line is going to be y equals x, so the line that sort of goes a diagonal 45 degrees. And this line is going to be y equals rx plus 1. So what I'm going to do is I'm going to think about how these lines actually interact in the middle. This means that the slope of my line here is r. And this means that the y-intercept is 1. So that means that up here I have a 1. This distance is 1. But now remember the definition of slope. It is rise over run. So now I can think about how I proceed from one point to the next point on this line. But I also have this y equals x that I can sort of reflect things off of. So here's an interesting idea. If I actually go horizontally across, because this line is where the y-coordinate is equal to the x-coordinate, that means that the x-coordinate of this point, that corresponds to this distance, is also going to be 1. In fact, every time I reflect anything off of my y equals x, I will get the exact same x and y coordinates. So then I can go up more and to the right again. So now I've noticed that this is actually smaller than my first step. What is it going to equal? Again, remember that the slope of this line is r, which is rise over run. So for every point on this line, the rise over run will correspond to r. So how did I get from here to there? I have risen this much and I have ran 1. The slope has to be r, which means that this distance actually has to be r. Let's review that. Going from here to here, rise, r over 1 is equal to r. Great. Let's do this again. So here, again, reflecting in the diagonal, I know that this is also going to be r, but I'm going to look at the next step, which is smaller still. So going from this point to this point, rise over run, so rise over run, but in this case, run is equal to r, has to equal to r because it has to be the slope of my actual line. So what is the rise equal to? Well, if I cross multiply within this equation, I can see that rise is going to equal to r times r, or r squared. So here, I'm going to have r squared, and also here, I'm going to have r squared, and so on and so forth. So this is really fascinating because, look, I'm already acquiring this kind of terms in all of my horizontal and vertical distances here. So if I think of how I can proceed either vertically or horizontally, it doesn't really matter, between this point at the beginning and this point at the end, what do I have? So let's say we want to go horizontally. What is my total horizontal displacement? Let's say I started here. Horizontally, this is at 0, right? And then I went 1, and then I went r, and then I went r squared. And if my pattern is to repeat, I will simply be adding steps of smaller and smaller sizes that all correspond to the actual powers of r, and so on, right? Now, because they will get infinitesimally small, I cannot actually ever stop anywhere. I need it in the limit to reach this point of intersection. So this is one way of counting my horizontal displacement. The other way to count it is to actually think about what are the coordinates of this point of intersection. So let's figure that out. Point of intersection. How do we generally compute the actual points of intersection? What happens at that point is the two lines meet, which means their equations are actually equal to each other because they have to arrive at the exact same point. So I'm going to have that rx plus 1 is equal to rx. Sorry, not rx, just x. And now I can solve this for x. I'm going to skip the solving steps because they're pretty trivial, but what I'm going to see at the end is that x is equal to 1 over 1 minus r. So this is the x-coordinate of this point. Let me write this down. The x-coordinate here is 1 over 1 minus r. Now, the horizontal displacement between here and here was equal to this, and the x-coordinate of this point is also that, which means that those two expressions have to, in fact, be equal. And here is where we arrive at our first formula for determining the sum of the geometric series. The sum of the powers of r from 1 all the way up to the infinity, the infinite sum, is equal to 1 over 1 minus r. This also gives us some idea of why this particular formula has a certain restriction on it. And the restriction is the fact that your r better be between 0 and 1. And that is the case because, look, if my slope r was bigger than 1, this line has slope 1. So if the slope of the other line is bigger than 1, it means that this other line will be steeper, which means that these two lines will never meet. So I'm never going to have that point of intersection in the first place. Purely algebraically, looking at this expression here, I can see that r cannot be equal to 1 because otherwise I will be dividing by 0. But it is not actually clear why r has to be less than 1. It could be bigger than 1 after all. It's only the geometric picture that actually provides that kind of justification. Okay, but overall, this is now the formula that I have for actually computing the sum of geometric series. Okay, now this is for the infinite ones. What about the finite ones? So if I have something like this, from 1 all the way to r to power n, where n is some fixed number, so I have a stopping point in my sum somewhere. What is going to be the actual total result of summing up these numbers? Let's try to derive the formula. So in order to derive the formula, I'm first going to think about what is rs look like. So if I take this entire sum and I multiply it by r and I open up the brackets. So let's take a look. R times 1 is going to be r. So I'm going to write it under the r term here. Then again, back to my sum times r, right? R times r is going to be r squared. R times r squared is going to be r cubed. Times r cubed is going to be r to the 4th. So I'm seeing that multiplying by r simply increases the power of each single term all the way to the last term I'm going to multiply. R times r to the power of n is going to be r to the power of n plus 1. And what I'm going to do next is I'm actually going to subtract these two equations from each other. So on the left-hand side, I have s minus rs. And what do I have on the right-hand side? I'm going to have this entire expression minus this entire expression. But of course, a lot of my terms are similar. So r minus r will cancel. R squared minus, apparently I can't write them down properly. R squared will cancel out. R cubed minus r cubed will cancel out. All of these guys will cancel out, but there's no match for the last and the first. So we're back into the sort of telescoping sums area, right? So what I'm going to have is this beginning term 1 minus this last term, r to the power of n plus 1. Now remember, my goal is to figure out what does this actually sum up to. So my goal is to figure out the value for s. So now I'm just going to take this equation and I'm going to solve it for s. let me rewrite it over here. S minus RS is equal to 1 minus R to the power n plus 1. Let's factor S out from the left-hand side. This will leave me with this expression, and then I can just divide everything by 1 minus R. So overall, I'm going to have 1 minus R to the power n plus 1 over 1 minus R. So now for the sake of completeness, let me just write out what S was. S was 1 plus R squared all the way up to R to the power n. And now the formula that we have for it up here is 1 minus R n plus 1 over 1 minus R. So my formula for the finite geometric sums is given by this expression. So notice the differences and the similarities between the two formulas, the infinite and the finite one. The denominator is actually the same, and the differences are, of course, this sum goes on forever, and we can compute it only between 0 and 1, whereas this sum stops, and apart from r equals to 1, we don't have any other restrictions on which r's can be used within this formula and which ones cannot. So let's see how this actually works out within the examples below, and how we can utilize both of these formulas to actually compute some calculations. So first up, we have 1 plus 1/2 plus 1/4 plus 1/8, and so on. So notice that my r here is 1/2. As I move from one term to the next, I multiply by 1/2 every single time. So this is certainly geometric series, and it's a geometric series where r is equal to 1/2. Now then, I have to also decide, is it a infinite or a finite one? And I can see that I go on forever, which means that I'm in the case of the infinite geometric sums, so I will be looking to apply this formula. And then the final thing we have to check is to make sure that this starts up at the 0th power. This one corresponds to r to power 0, and it indeed does. So in this case, this is just a direct application of our formula. So what do we have altogether? We're going to have 1 over 1 minus r, which is 1/2. So if I simplify all of this together, I'm going to have 2 as my final answer. So that means if I take all of these numbers between 1 and infinity in this pattern of every other number being 1/2 of the previous one, the total sum is going to equal to 2. This can be quite a lot to wrap your head around, simply because the sum itself is infinite, so it goes on forever. But what this is saying is, although it goes on forever, it will approach 2. It will never exceed 2, and it will just get closer and closer and closer to 2. You can pull out your calculator and add a bunch of these terms just to see that the intuition sort of holds. But there is another interesting way to view this. Now, I'm going to draw a picture not for this entire sum, but only for this infinite portion of it. So I'm going to take 1 away from it. So if this entire sum is equal to 2, I know that this portion of it has to equal to 1, right? Because 1 plus 1 is then 2. So the way to view it is, let's take a square. Let's take a square, and I'm going to assume that the side length here is 1. So now I am interested in, what does this sum represent? So notice that my first term is 1/2. I'm going to think of 1/2 as the area within the square. Well, if the square has a side of 1, that means that 1/2 is going to be exactly half of its actual area. So 1/2 is going to be, let's say, this portion of my square. Okay, so this corresponds so far to my 1/2 here. You know what? I'm just going to write in the middle here. 1/2. Excellent. Next up, I have to add 1/4. Well, I've already shaded this area, so I sort of have this 1/2 to work with, and I need 1/4. I need 1/2 of the remaining area. So I'm going to shade that in as well, and this will represent the next term being 1/4. The next up is 1/8, so 1/2 of what I just shaded, and I still have this 1/4 available, right? So I'm going to shade 1/2 of that, and that will represent 1/8. 1/8, and so on and so forth. So what I'm seeing is, if I work within this square, what I'm doing is shading 1/2 of the available area every single time, and I am doing so forever, which means that eventually I will cover in the limit the entire area within my square, which is equal to 1. So this portion of the sum is in fact looks like it equals to 1 geometrically as well. This is a very good argument to persuade yourself that this will certainly not be more than 1, because by this kind of shading, I can never get something outside of the square, so I'm certainly not going to exceed its area. But also, again, doing this forever hopefully persuades you that in the limit, we will in fact get the area equal to 1. These types of geometric arguments are possible for all kinds of shapes within the geometric sums that look like that. So we will actually see one later on as well. Okay, next up I have 1 plus 2 plus 2 squared all the way to 2 to power 10. So I have my final term, which signifies to me that I am going to be using this formula. My sum also starts at 1, which is in the proper shape. So I can apply this formula directly. I can see that my r is equal to 2 and my n is equal to 10. So if I apply my formula, what I'm going to get, let me just move the square bit out of the way, is 1 minus r, which is 2 to power 10 plus 1 over 1 minus 2. And you can compute this as a number or leave it as is. You can see on the bottom you're going to have -1, which is probably a little more concerning than it should be because you're thinking like, oh, I'm getting a negative number. But notice that the number on the top is also negative. So you're going to get a negative over a negative, which is of course a positive. So we're in good shape here. Next up, I have 1 plus a quarter plus 1/16 plus 1/64, and so on. So this again is of the form of our infinite sums. So I just have to determine what my r is. I went from 1 to a quarter, so divided by 4, and then to 1/16 divided by 4 again. So my r here is going to be 1/4. And then plug it into a formula. I get 1 over 1 minus r, so 1 minus 1 over 4. And if I turn it all around, I'm going to get 4/3. Because of, so the bottom here is going to be 3/4, and then 1 over makes it flip on its side. So I'm going to get 4/3 over here. We can once again start with the square, but we're going to have to fill it out differently. Again, I'm going to sort of ignore this one and focus on this sum. According to my answer, 4/3, this sum should equal to 1/3 to give me the exact same outcome. So what I'm going to have is I can start with a square as I have before, but now I have to come up with a way to cover 1/4. So that means I'm going to have to divide it into fourths like this, and I'm going to shade in 1/4 of it, so one of these pieces. Notice that every piece I've identified is actually a quarter. So for example, this one is a quarter as well. 1/16 is a quarter of a quarter, so I have to do the exact same process to my next square. So I'm going to divide this into quarters as well, and I'm going to take a quarter of that, which corresponds to 1/16. Okay, and I can do this again. So if I divide this guy into fourths, this little piece will represent 1/64, but it's now actually too small for me to write the number in, and so on and so forth. So again, you can see that you're never going to escape the square, but now how do we visually see what the actual answer is going to be? In this case, it was easy because I filled out the entire square, so I knew that the summation here was going to be equal to 1. But what about the summation in this case here? Well, let's take a look here. This structure is actually quite interesting. So what you have, if you sort of squint a little bit, you will see that these squares form the exact same shape as these squares on the top and these squares on the bottom. So what we actually end up with is we have this exact same structure here, here, and here, which means that the shaded portions correspond to exactly 1/3 of the square, which is exactly what the sum is equal to. And then 1 plus 1/3 is going to give us 4/3. Aren't geometric arguments beautiful? I think so. Okay, let's take a look at this next one. 4/3, 4 to power 3, 4 to power 4, all the way up to 4 to power 50. So I have an nth term, which means I am in the finite sum case, but now I'm not starting with 1. I'm starting at 4 cubed. So I'm starting kind of like in the middle of this summation over here. There are 2 different ways to actually approach this, and it is completely up to you which one you prefer. I will show you both methods. So one way to do it is to say, okay, I am actually going to factor out 4 cubed out of this expression. So I can take 4 cubed out, and what I'm going to have left is, if I took 4 cubed out of 4 cubed, I'm going to have 1. If I took 4 cubed out of 4 to power 4, I'm going to have a 4. And then I'm going to have a 4 squared, 4 cubed, and so on. And taking 4 cubed out of 4 to power 50, I'm going to have 4 to power 47 left. Once you have this, you can apply the formula directly to what's inside the bracket and not forgetting to multiply by 4/3 on the outside. So let me just move this over. So what we're going to have is 4 cubed times, and then again, the formula applied to this case inside the brackets. Clearly r is 4, and in this case n is 47. So I'm going to have 1 minus 4 to power 47 plus 1 over 1 minus 4. That's one way to proceed. The other way to proceed is instead to supplement it with the missing terms by adding and subtracting them. So what I would really like to see instead, let me do it in different color here, is I would like to see 1 plus 4 plus 4 squared plus 4 cubed and so on, all the way up to 4 to power 50. But I obviously don't have that. I am now injecting some new terms into the summation. So this is a summation I already have. These are the new terms that I'm adding just to have it match to the formula. If I'm adding these terms, I have to also subtract them back because I need to be able to write this equals to that, right? So these 3 additional terms have to be subtracted out. So minus 1, minus 4, minus 4 squared. But now I can apply my formula to this first portion and then simply leave this as subtraction afterwards. So in this particular case then, my r is 4 and my n is 50. So I'm going to have 1 minus 4, 50 plus 1 over 1 minus 4. And I should remember to subtract all of the terms that I've added in just so I can use the formula. I know that these two answers don't look the same because we've derived them using different methods, but they are actually the same value, which you confirm by using a calculator. Whichever way you prefer, by either adding and subtracting or by factoring out in this case, is completely up to you. I'm going to leave this example for you to do as additional practice. It uses the exact same logic as part D, so I strongly encourage you to do both ways to really figure out which one you prefer to use personally. And this last one here, so I have 3 plus 9 plus 27 plus 81, and this goes on forever. So what is my r here? I go from 3 to 9, so I multiply by 3. And then I go from 9 to 27, I multiply by 3 again. So my r here is 3. And it's an infinite sum, so I'm in this case up here. Notice that, again, this is only applicable if r is less than 1. Whereas in our case, r is equal to 3, so I cannot apply that formula. What else can I reason out? Well, let's see. I'm adding this up forever, and I am increasing my numbers every single time. So I am adding bigger and bigger and bigger numbers as I go along, and I'm doing so for infinity. So this becomes very clear that this sum will actually tend towards infinity. This will not have a finite number as the answer, as opposed to the sums of the same format when r was less than 1, because these numbers keep increasing forever and they keep getting added on to each other forever and ever. So we've now worked with the sums, we worked a little bit with products. Let's recall what a factorial is, because this is something that will come up in the proofs using induction and recursion that we're going to look at next. Recall that a factorial is defined as the multiplication, the product of all the numbers from the factorial number all the way down to 1. And we also define 0 factorial to be equal to 1. In terms of counting, remember that factorial represents the number of ways to arrange and distinct objects in a line. Just for the sake of some practice, let's compute some of the first factorials. So I have that 0 factorial is 1. 1 factorial is, we start with this number, work all the way down to 1, which is just 1. 2 factorial is 2 times 1, so that's pretty straightforward. It starts getting a little more interesting when the numbers are bigger. We start with this number and we list all the numbers all the way down to 1. And then we can compute the total product by simply multiplying them all together. Now, we also do begin to notice some patterns occurring within the factorials themselves, right? And so we begin to actually notice them pretty early on as just writing these out. You see here, as we've observed before, that this is the exact same expression, which means that instead of computing 4 factorial as just multiplying all the numbers in a line, I can say that it's 4 times 3 factorial, which is 6. So 4 times 6, which is easier to compute. You're just multiplying 2 numbers that are by themselves, 24. So let's see, what about 5 factorial? I have 5 times 4 times 3 times 2 times 1. But again, I can notice that this is what I've already computed as 4 factorial. So I can simply plug that number in there. 5 times 24 is 120, and so on and so forth. So for example, 9 factorial is 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1. Notice though, that when you're doing them in a row, it's actually easy to use the previous structure to compute the next number. But if you're just giving one lone factorial, there is no previous computations that I can rely on, for example, for 8 factorial to actually utilize. So if you're only computing 1 factorial directly, you actually will compute it in a line. This kind of process where you compute everything previous to it only works if you've actually done the previous computations. Let's see how we can work with some factorials. I strongly encourage you, especially because a lot of these exercises are from before, to pause the video here and actually go through them yourself to remind yourselves about how factorials and simplifications with factorials actually work. Okay, so let's say we're looking at this, 6 factorial over 3 factorial. So I have 6, 5, 4, 3, 2, 1 over 3, 2, 1. So I notice, of course, that an entire chunk of my 6 factorial gets factored out, and I'm left with 6, 5, 4, which is not anything that we actually have the notation for in this course. Going through this, I'm going to leave it up to you. Let's take a look at this one, for example, n plus 2 factorial divided by n factorial. So n plus 2 factorial means I'm taking all the numbers from n plus 2 all the way down to 1. And n factorial, of course, means I'm taking numbers from n all the way down to 1. And I notice that this entire chunk appears again. So what I have left in the end is just n plus 2 times n plus 1, which is much nicer to compute because you only have to multiply 2 numbers as opposed to multiplying n plus 2 numbers together, multiplying n numbers together, and then just dividing the 2. So this will save you a lot of computation. Let's see how factorials can live within summations, because this is something that we're going to be working with going forward. So I have I times I factorial. My index starts at 1, so I will just iterate over my indices, and I will add all of the consecutive terms together. 2 times 2 factorial plus 3 times 3 factorial, and my sum goes up until 5, so I am nearly there. And once I hit 5, I am done with my summation. This factorial, I do believe we've also seen it before, but let's expand it out. N plus 1 factorial means n plus 1 times n minus 1 all the way down to 1, divided by n minus 1 factorial, so n minus 1, n minus 2, all the way down to 1. And again, I notice that this entire chunk can actually disappear, and what I'm going to have left is n plus 1 times n. These types of simplifications are going to come in particularly handy when you then also have to do something with the final result. So here I have a sum from 1 to 5 of this exact same expression as I've just simplified. So instead of writing it out as a summation unsimplified, what I'm going to do is first use my part E of this question here and rewrite the internal term as the simplified version. So notice that here I have I as the index, so my general term that appears inside will have to be in terms of I, but it's going to be the exact same shape, I plus 1 times I. Okay, excellent. Once I have that, now all I have to do is actually run over my indices from 1 to 5 and expand this sum out if I want. Or, using our previous techniques, 5 is a small enough number, but if you had a bigger number, it would be smarter to actually expand the internal terms out. So let's do that for the sake of showcasing how this would work in generality. So if I open up the brackets here, I get I squared plus I squared plus I. And remember that I have formulas for I squared and I that I can apply separately. So now I have from 1 to 5 I squared, and from 1 to 5 of I. Remember the formulas from a few pages ago? I'm not going to flip back. You should probably have those handy for future use. I will just simply write out the answer. The sum of squares formula tells me that I'm going to have n, which in this case is 5. That's my last term here. So 5 plus 1, 2 times 5 plus 1, all over 6, plus, and then the formula for simply the numbers is 5 times 5 plus 1, all over 2. And there we go. Again, this sum is small enough that if you just expanded it out, you could compute without too many more operations than this. But if instead of 5, we had a 50, this would have been impossible to do by hand, and you would have had to actually rely on the formulas to tell you the final answer. Notice also that we started with factorials, but we ended up utilizing the summations that we've already worked out at the beginning of this class. This is the beauty of simplifying before you actually try to expand the sum out to see if it looks like something we've seen before, and therefore formulas from before can actually apply now. One thing to remember is if you have a factor inside a factorial, you cannot just cancel things out that look similarly. 2n factorial is very different from n factorial. So 2n factorial means we start with 2n and we work our way down one by one. So somewhere along the way, we will hit n halfway through, and then we will proceed to decrease all the way down to 1. So if we divide this monster by n factorial, so n minus 1, and so on and so forth, I can see that the tail of it gets canceled out, but the beginning of it is not something sort of very concise or very precise to be written out. So the beginning of it will simply be the product of the numbers between 2n and n plus 1, that's the next term here, and that's just it. So this expression doesn't get simplified very nicely. Let's take a look at this sum. This has some interesting structure. So I have I factorial minus I minus 1 factorial, and I'm going from 1 to 50. So let's write out the first few terms. So what I'm going to have is 1 factorial minus I minus 1, so 0 factorial, and that is going to be my first term. Okay, so this is the first term altogether, plus my next term. I is equal to 2. I'm going to have 2 factorial minus 1 factorial. 1 factorial. That's going to be my term 2. So let me just write out I equals 1, I equals 2. The next one, let's say I equals 3, and maybe let's do one more. So what we're going to have for I equals 3, what do we have? 3 factorial minus 2 factorial. For 4, we're going to have 4 factorial minus 3 factorial, and we already notice that this negative in the middle will actually serve to cancel a bunch of stuff out. So this 2 factorial will cancel off together with this negative 2 factorial. This 3 factorial will cancel off with this negative 3 factorial, and so on. So we have a pattern that we can use to our advantage. What's going to happen at the very end of this summation? So you might prefer to write down the last, let's say, 2 terms. So let's say I is 49 and I is 50. So for 49, we're going to have 49 factorial minus 48 factorial. And then for 50, we have 50 factorial minus 49 factorial. Notice that at the beginning, so let's cross out what we can. 1 factorial minus 1 factorial, 2 factorial minus 2 factorial, 3 factorial minus 3 factorial. And notice at the end, 50 is the largest we're going to get because that's our last term and we're plugging that into here. So I'm not going to be able to cancel this out from anything before because it's the first time it's occurring. But 49 here will be canceled with this 49 here. Whereas, let me cancel them out. Whereas 48 here will be canceled with 48 from the previous term, and so on and so forth. So everything else will actually get canceled out. And the only terms we will have left is going to be this negative 0 factorial that happened in the beginning because it was the smallest possible term in the beginning, and everything else after that was increasing, so we will never have seen it again. And this 50 factorial, because it's the largest one occurring at the very end, and everything that came before it would have been smaller. So now, All I have to do is compute this. 0 factorial is 1, so what I actually have is 50 factorial minus 1. I'm not going to write this out as the answer. This is much better, once again, as the actual answer because the logic of how it was obtained is clear. This is another example of the telescoping sum that we've seen before. We start with this giant telescope, and then we collapse it to just the beginning and the end term here.